Hello everybody, it's Stereo Police. Welcome back to Audiophile University Lecture 5. If you're catching this anytime, if you're catching this as soon as I publish it, you'll notice I've skipped Lecture 4. I'm going to get back to that. So there's going to be an in-between lecture that I have not published as of yet. This one I think is going to be super helpful and informative for audiophiles, because we're going to talk about terminology that's often discussed in reviews and by reviewers and by manufacturers. And that would be total harmonic distortion, or sometimes abbreviated THD. All right, so well, before I get into it, let me say this. I really encourage those of you watching this to stick with me through every single slide, particularly if you're a non-technical audiophile, because it's all leading up to something at the very end. And to me, it's pretty profound when you actually understand what THD is and how it's measured. It's going to make you that much better as an audiophile to understand this stuff. The lecture that I skipped in Lecture 4 was really the difference between AC and DC. And I'm just going to cover it in a very cursory manner right here. Just stare at these waveforms on the right, just for a second. Now, we have talked about voltage in previous Audiophile Universities. I'm going to talk about that again. It is a form of pressure that causes charge to flow. And there's a type of voltage we call DC, another type of voltage we call AC. Actually, C stands for current. So voltage can be alternating, and when the voltage alternates, the current that it causes to flow will alternate in kind, at least in a linear circuit. And if we were to plot the voltage, and when I say voltage, you can just think of, let's just think like a 9-volt battery right here. That could be, 9 volts. There's one right there. And we were to plot this over time, and let's say this time period's 10 seconds. It could be 10 hours, 10 years. We'll change that in a minute. Right now, let's call it 10 seconds. And you were to put a voltmeter across it, you would measure just a constant voltage. As time ticks on, the voltage will not change. And we call that DC for direct current, meaning if that voltage were applied across a resistor, the current flowing would be direct. It would not change. If we were to change this time right here to, say, 10 hours, and that voltage was across, say, a light bulb, there's lambda, our symbol for light. Well, that little old 9-volt battery, not that strong. It's going to deplete itself. It's going to deplete itself of chemical energy. So this line will no longer be flat. At some point, the voltage is going to start to drop, and then it's going to tank. So over time. So the battery gets weaker and weaker and weaker. We've all experienced that. Well, that's a variable voltage, and that's a form of AC. A form of it. Not what we're going to talk about. Meaning that if that battery was placed across that light bulb over 10 hours, the current that flows initially is going to be about the same. At a certain period of time, as that voltage drops, the current will also drop because that pressure is dropping. That would be AC. The current will alternate over time. That's not exactly what we're talking about, but that's sort of an analogy. In reality, when you think about, plugging an outlet into a wall, what we receive, if we look at voltage over time, is something more akin to what looks like this, called a sine wave. And it's just basically, and this is what comes out of the wall is called 60, in the US, in Europe it's 50, but 60 hertz, meaning 60 cycles per second. And a cycle is when the voltage rises to a peak, falls to zero, falls to a negative peak, and comes back up to zero. That's one cycle. And 60 hertz means it repeats this cycle 60 times in a second. That's it. So if I were to take a snapshot of this, and you could do that on an oscilloscope, and you could measure the voltages, just like this battery, you could measure voltages anywhere along here. And let's say this achieves 9 volts here. This is 0 volts. And in between is the voltages in between, 1, 2, 3, 4. And then it reaches a peak and it starts to fall again, blah, 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 and then 0. Then it goes negatively down to a negative 9 volts. So -1, -2, -3, and then it reaches its peak of -9 volts and starts to rise again to 0. Now, what does negative mean? All that means, and typically we draw a voltage source, an alternating source like this, instead of the battery up here like that. And all that means, I'm going to draw a resistor for a load. All that means is during the positive half cycle, let's say, current is going to flow one way because we have positive and negative across our resistor, and we're going to use conventional flow here. So current will flow in this direction, just like if we had this battery hooked up, positive and negative. On the other hand, during the negative half cycle, it would be similar to as if I had the battery reversed. If I just flip the battery, I have negative and positive. Well, current's going to flow from positive to negative, so the current's going to be reversed through the load. That's all I want to say about that. It's just conceptual. I want to talk about that in lecture, what did I say? Lecture 5. In lecture 4, I want to talk more about that, although I've done a pretty good job here, I think. Okay. Now, very briefly, I want to talk about, you've heard terms time domain and frequency domain. We don't really need to know much about this, but what a domain is, if you think about domains like kings and kingdoms, survey your domain. It's the real estate you own, sort of. It's just looking at an area. So in the time domain, we're looking at an area of voltage in relation to time. That's it. How voltage changes in relation to time. Coming up in a little bit, we're going to look at something called the frequency domain. And it's the same thing, except we're going to look at voltage or some kind of a level here, an amplitude. But instead of looking at time, we're going to look at the frequencies. And these are frequencies that make up the signal. Now, in the case of a single, and we're going to get into this, in the case of a single sine wave, and sine waves are the building blocks of every signal. It's like a sine wave is a Lego block. It doesn't get any, it doesn't get any more fundamental than that. And you can build anything you want out of the Legos. And the Legos come in different sizes, let's say. It's a bad analogy, but they're still Lego blocks, and that's what sine waves are. So if we were to look at just a single sine wave in the frequency domain, and this would be the amplitude of the level, so let's just say it was 9 volts arbitrarily. All we would see is a single line here. It would have an amplitude over here of 9. And down here on the frequency domain, what's the frequency of this? Well, let's just say it's our power frequency, from our wall. So it's 60 hertz. Hertz means cycles per second. Well, down here, this would be 60. That's it. That's the frequency domain. It's no more complicated than that. Let's look at some images taken from Stereophile. I like Stereophile magazine. I enjoy that publication. This is a 10 kilohertz. Remember what hertz means, cycles per second, 10,000 cycles per second. Now, this was called a sine wave, and we're looking at a square wave, and it's self-explanatory. It's a signal that looks more like a square. 10 kilohertz. Now, what domain are we looking at it in? So we have our amplitude or our voltage here. And what's happening along this axis right here? In mathematics, we call it ordinate and abscissa, but I'm just going to call it the x and y axis for, I can refer to it, but x and y axis. All right. Well, look down here. We're looking in microseconds. Well, seconds. Time. This is the time domain. We're seeing how this signal changes in time, and it looks like a square. Here's another example of a sine wave, and we're looking at it in the time domain. I don't even need something down here to tell me it's in seconds, because we're looking at how this thing changes in time. It's pretty clear. This, by the way, is also an indication of distortion, what the distortion looks like in the time wave. I'm not going to get into that right now. Let's look at the frequency domain. How do I know it's the frequency domain? Because the x-axis is given in frequency. This is hertz, cycles per second. And the y-axis is just a level. Oftentimes, engineers like to use the decibel. And a decibel is just a fancy ratio, and it's just a way to take really high levels and compare them to really low levels and squeeze it all into one little graph. So in other words, let's say you had a really super high level and this little teeny weeny level down here that you can barely see, and I want to look at it on a graph, and I'm looking at it as, for example, voltage. Well, that's not very handy. So if I put it into decibels, let me erase that. If I put it into decibel form, instead of voltage, it's going to squeeze things down a little bit so I can kind of get a better idea. I can look at them more visually and squeeze it all into one chart. So it doesn't really matter. This happens to be dB, dBr. Don't even worry about it. It's just the idea of knowing that the y-axis is the amplitude of something and the x-axis is frequency in the frequency domain. All right. And we're also looking at, this is a stereophile. We're looking at the same amplifier, Luxman M10X. I don't know what that is. And we're looking at the spectrum. Okay, so this is of the 1 kilohertz sine wave. I think it's this sine wave right here. Now remember when I said a sine wave should just look like this. And in this case it's a 1K sine wave, so there should be one line here at 1 kilohertz. So if there should be only one line at 1 kilohertz, how come I'm seeing, and here it is right here, you see it's 1K, and here's our line. How come I'm seeing this stuff? And what is it? Well, folks, these are called harmonics. And this, you're looking at the distortion that's been introduced by the amplifier. So this stuff right here is what makes up this stuff right here. I'm going to get into that. So what basically, when you input a signal, and let's say that's our 1 kilohertz pure, as pure as we can get, low distortion, let's say 0.000002%. And we pass that signal through a nonlinear component or system. It could be a transistor, it could be an entire amplifier in the case of we're measuring an amp. And the amplifier is going to add distortion and noise. It can't help but to do so. There's no such thing as a perfect system. And what we want to know as audiophiles is, well, how much? How much distortion? I'm not going to get into noise today. I'm not going to worry about that. We want to know how much distortion is this amplifier adding as a specification. It's going to distort it. No system is perfect. Okay, and that's why we often look to the frequency domain to figure out how much distortion is added. Now let me get into something right here. I'm going to keep going with this. Like I said, again, all my sources are right here, and I encourage you to check. If you're interested in this stuff, check out these sources. So let's just say we have, it doesn't matter the frequency, it's irrelevant. It's just, let's say we have a pure sine wave right here, and let's say for theoretical purposes, it's perfect. There's no distortion. And this is the time domain. So this is how the sine wave oscillates in time. Okay? Now, let's look at this same sine wave in the frequency domain. Now let's just say this is 60 hertz, like our power coming out of our wall. If we look at it in the frequency domain, well, we only have one component. It's the 60 hertz frequency. That's it. It's perfect. There's no other components to this sine wave. There are no harmonics. Well, let me stop right there. Well, you know what? Let me just come down here for a second, and I'll go back. Let's say we look at an imperfect sine wave, a sine wave that's been distorted. Well, what distortion is the addition of harmonics by our amplifier or by our nonlinear system. It's going to add harmonics and distort that wave. So here's our time domain. And you can't tell much in the time domain. So we've got to do something called a Fourier analysis to figure out, okay, what are these components that are causing this odd-looking sine wave, the distortion? They're right here. So remember, we input to the system a perfect sine wave, and that's going to appear right here as we call it our fundamental, right here. Well, that's going to come out. That fundamental is still here somewhere. But we've also added all this other stuff called harmonics. That's why we call it harmonic distortion. We've added these harmonics to cause this sine wave to look kind of funky. It's been distorted. So that's called harmonic distortion. Now, before we get into something that I find just really fun, fun from a nerd standpoint of view, let's talk about Fourier analysis and Fourier synthesis. You've got to bear with me here. This is important. There's something called Fourier synthesis. I'm not going to go deep here. It's very fundamental, and everyone should be able to understand this. Fourier synthesis is a process where we can build, and we're going to build this sawtooth wave right here. Looks like a sawtooth, right? And this is in the time domain. We're looking at the time domain here. And remember I told you sine waves are just little Lego blocks. We can start, it's not a great analogy, but it's the way to look at it. We can start with a fundamental. And that fundamental is going to have likely the same frequency as the sawtooth we're going to build. But you can see the fundamental looks nothing like the sawtooth. So now we need to distort in a good way, because we want to build the sawtooth. We need to distort the fundamental to achieve the sawtooth. Well, how do we distort it? We add harmonics. Now watch the process. We're first going to add called a second harmonic, which is twice this frequency. Then we're going to add a third harmonic, which is 3 times the frequency, then a fourth harmonic, which is 4 times the frequency, and so on up to the 20th harmonic. And you can see how the signals start to change and start to look more and more like the sawtooth until we get to a sawtooth that we're happy with. That's called, and by the way, when we add these harmonics, we can do 2 things. 3 things really. When we add them, we can add them, you see we're adding the second harmonic is twice the frequency, but we can also, when we add it, we can adapt the amplitude, we can change the amplitude, we can make it a higher level or lower level. And we can also add it by shifting the phase, by moving it in time, a little bit left or a little bit right. Too complicated for today, but the point being is we build, like little Lego blocks, we build the sawtooth. That's called synthesis. Have you heard of a synthesizer? It's a musical instrument. This is what a synthesizer does. Synthesis means to build. There's an opposite type of thing called Fourier analysis. Analysis is the opposite of synthesis. And in analysis, instead of building this thing, we're starting with this thing and we want to find out where the heck it came from. So it's the opposite. So let's say we start with this funky looking wave right here, and we're going to analyze it. That's where the word analysis comes from. And we're going to break it down into the sum of its parts. And remember the harmonics. We can do this it's actually very easily, fairly simple mathematically. Well, I shouldn't say that. It's something that every second year, I think, well, I learned it in my second year of engineering, but so I guess it's not so simple. So how do we figure out where this wave came from, this signal came from? It looks kind of weird. It's not a sine wave. It's something else. Well, through analysis, we figure out, okay, here's our fundamental. It's got it's got a frequency, it's got an amplitude, and a phase. I don't want to get into phase. And then it's got this harmonic and it's got that harmonic. And we analyze it to figure out the frequencies of the harmonics, the amplitudes of the harmonics. Forget phase. And now we know what built this signal, how it was built. This is exactly what we're doing when we analyze total harmonic distortion. If this thing here was supposed to be a sine wave, and it was distorted in this way, well, we figured out that this, it was supposed to look like this, but we figured out these things were added to it to create this mess. This is where our harmonic distortion came from. And ultimately, this is leading up to, I'm going to show you how to determine the total harmonic distortion as a percentage, like we always see as audiophiles. Okay, and this is just another example of Fourier analysis. This time we're building a square wave. So we have a fundamental, and then we have a third, and a fifth, and a seventh, and a ninth. So we don't have to add we don't always need all the harmonics. This time we're adding odd harmonics. The third, the fifth, and the seventh. There's no even harmonics even in here, like 2 and 4. And see, if we can, that's another way we can do things. We can skip harmonics when we build things. All right? So I've already talked about this right here. Remember, these things right here are the harmonics that, when added to the fundamental, created this distorted waveform. And here's something that I already created. This was the fundamental the pure input signal that went into the nonlinear system, let's call it the amp. And what came out of the amp was this mess. And what caused it? Okay, so our fundamental is here. I wish that's, ideally that's all I want to come out, but that's not what's going to come out. What caused this mess? What was the addition of the harmonics. And we do that through Fourier analysis. Just like I talked about. We're going to figure out this stuff. All right, so harmonic distortion, or total harmonic distortion, is just simply a ratio. It's a ratio of all the harmonics, simple math, folks, divided by the fundamental times 100, and that'll give us a percentage. Now, before I get into doing a real-life example of this, not real life, but a fictitious example that I made up, for those of you who kind of forgot what ratios are, and it's really worthwhile to go through this because I'm doing this for non-technical audiophiles, no offense. I want to go back and just talk about ratios. It's really important to understand this. Now remember, ultimately we want to calculate a percentage, percent total harmonic distortion. And it's the percentage of all of this stuff to this. What percentage do we have? 1%? 10%? 0.0002%? That's the question we're asking. So let's talk about what a percentage is. And this could be for anything, Percentage of two numbers. Percentage of people wearing red shirts relative to everybody in the room. So let's just say there's 485 people wearing red shirts, and there's a total of 1,684 people in the room. It's a big room. What percentage of these people are wearing red shirts? Well, percentage is the ratio of the part to the whole. The part are the people wearing the red shirts. The whole is the whole number of the people in the room, including the people wearing the red shirts. So 485 divided by 1684 is 0.228. Now that's just a decimal number. To get percentage, we need to multiply by 100. 28.8%. That's our decimal multiplied by 100. That's it. And this is exactly what we're doing with total harmonic distortion. This is just a little graph if you want something more intuitive to look at. Here we're asking what percentage is 7 of a total of 12. Now we all know intuitively 6 out of 12 is 1/2, or 50%. But now we're asking what percentage is 7 out of 12. 7 divided by 12 is a decimal 0.58. If we multiply that by 100, we get 58% instead of the 50%, which would have been 6. Let's return to harmonic distortion. What percentage of this stuff exists relative to the fundamental is what we're asking in this case. That's what we're asking. So, total harmonic distortion is a ratio of the harmonics to the fundamental times 100%. And let me just show you real quick. This is the actual formula for it. Where's my source on this? Darn it. I need to add, I'll add a source to that. I'm sorry. Anyway, I must have deleted it by accident. I'm going to get to this in a minute. All right, so it's the ratio of the harmonics to the fundamental times 100. But unlike our previous examples, we have, instead of just one thing, we're doing a ratio of one thing to another. We've got many things here. So we need to add them up. Now, let's first calculate in this. Let me give you the example what we're going to do here. And actually, what I'm doing here, keep in mind, this is incorrect. We're going to get to the correct way in a minute. So I'm going to make up some fictitious numbers here. They're probably not that unrealistic. And instead of decibels, we're going to just use voltage. So let's just say our fundamental here is at 100 volts. And let's say our first harmonic, our second harmonic, F2, is 2 volts, and our third harmonic is 1 volt. Now, some of these things get more and more, less and less significant, and they don't really factor much into the equation. So we often cap these off at a certain place. So I'm not even going to consider these right here in the calculation. Let's say they get very insignificant. They're very low in level. So let's run the percentage of the ratio. Harmonics would be 2 plus 1, which is 3 volts. The fundamental is 100 volts. So that would be 3 divided by 100 times 100. Well, 3, what percentage intuitively is 3 out of 100? It's 3%. That would be 3% THD. Now, this is incorrect. It's close, but it's incorrect. Because that's not, in science and engineering, that's not how we add orthogonal signals. These are not just numbers. These are, I don't want to get too deep, but let me go down here. Our equation for THD requires that you take the harmonics, like the first one we talked about, which is, 2 volts, and the second, which is 1 volt. So this one here was 2, this one here is 1. And the way we add them together is we first square the 2, and we add it to the square of the 1, then we take the square root. And this is just a way of calculating an arithmetic mean of what we call orthogonal waveforms, which are, there's many definitions of this, but orthogonal waveforms, you can think of it as just waveforms that are upright and spaced apart. So like you can say orthogonal to this plane. Think about it that way. That's all. This is how we do it. And there are reasons for that. Just to get a more accurate, what we call mean or average of the combination of these things. So let's go back and do it the right way. So THD is the square root of 2 squared plus 1 squared divided by, divided by 100. That's THD, not percent. We'll do the percentage in the end, but it will be times 100 for percent THD, okay? So 2 squared is 4. 1 squared is 1. So we have the square root of 4 plus 1, which is the square root of 5, still divided by 100. You can fact check me on this. I've ran these numbers quickly, calculator today, but I think it's correct. So what's the square root of 5? It's 2.24. So now we divide 2.24 divided by 100, which we get 0.022. That's our ratio. We convert it to THD by multiplying by 100, so we get 2.2% THD. So it's not quite the 3 that we got when we did it the wrong way, but we're not just averaging numbers here, we're averaging orthogonal signals. So we have to do it this way. There you go. Stereo police. I've introduced a lot of terminology to you that I think will be helpful when you hear people discuss these things and read reviews. And now you know, and this is actually very, very simple. Conceptually, that is. Very simple, and I hope this brings value to your life as an audiophile. I sincerely hope that for you, and And thanks for joining me today. It's always an honor. Stereo Police.